Okay, so we just hit 1 minute after the hour. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the USGS Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or use the raise your hand feature in combination with your microphone and video camera if you choose. We're going to wait until the end of today's presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted and your video camera is off when you're not intending to speak. It's my pleasure to introduce today's speaker, Lisa Luna. Lisa is a Mendenhall postdoctoral research fellow at the USGS, and she studies weather-related landslide initiation problems in a changing world. She completed her PhD in georisks at the University of Potsdam in Germany in 2023. And in her research, she applies advanced data analysis methods to improve our understanding of landslide triggering conditions, track changes in the hazards over time, and predict when and where landslides are most likely to occur in the future. Lisa, thank you so much for joining us today. I'm going to go ahead and turn it over to you.
All right, thanks, Matt. Thanks for the introduction and also the invitation, and thanks to the organizing committee for coordinating this seminar. So today I'd like to share work that I did as part of my PhD at the University of Potsdam before coming here to the USGS. And in this study, I looked at the intensity and duration of rainfall that has triggered landslides reported in cities around the world. And I did that because I wanted to learn two things. First, if on a global scale, rainfall thresholds in cities are different from those that have been found for rural areas, and second, how different these triggering conditions might be between different cities. And so I'd like to take a moment to acknowledge my collaborators on this project. I worked with Maria Arango Corona, Georg Fay, Elizabeth Lewis, Or Ozturk, and Oliver Korup. All right. Let me just make sure I can advance my slides here. Perfect. So before we start talking about landslides, let's go ahead and talk about urbanization. So by 2050, 68% of people are projected to live in urban areas. So here we have a plot that's from the United Nations World Urbanization Prospects. We have global population in billions on the y-axis, time on the x-axis, and in brown we have the urban population, and green is the rural population. We can see from this plot that in 1950, the urban population was about half of the rural population. They were about even in 2008, and by 2050, the urban population is expected to be over double the rural population. And cities need to grow to be able to accommodate this influx of people. And as they grow, there we go. So as they grow, they often expand into steeper terrain. And this makes sense. If you're starting to develop a city, the easiest place to build is going to be in flatter areas, but as those flatter areas reach capacity, urbanization tends to expand up hill slopes. So this is an example from the city of Medellin in Colombia, a study published by Kuna et al. In 2023. And you can see on the DEM that the recent expansion, sorry, it sounds like someone needs to mute their mic. Okay, perfect. That the recent expansion, which is here in red dashed, is mostly located on these steeper hill slopes. And they found that the area exposed to landslides grew by about 250% between 1994 and 2018, whereas the total urban area grew by 33%. So we can see that the new growth is really predominantly in these areas that are more susceptible to landslides. And so as these areas become urbanized, they can change not just landslide exposure, by moving people into these areas, or vulnerability, perhaps changing people's ability to cope with the hazard, but can also change the hazard itself. So if we think of risk as the intersection between hazard, exposure, and vulnerability, urbanization can really act on all aspects to change landslide risk. And as an example of that, this is a nice figure from Deppiger et al. Published in Nature Sustainability, which shows some of the key processes that they looked at that were affecting shallow landslide risk in the Kivu Rift area of Eastern Africa. And so you can see some of these processes. So you may have started with people living in these flatter areas, but growing populations, and in this case, other drivers of mobility like conflict, then pushed people to expand up into steeper terrain. And as they do that, they of course need to make a livelihood. So you have mining industry, fuel wood extraction for cooking, agriculture, these road building. So this movement influences the exposure. So this also increases landslide risk, but some of these road building activities help to facilitate deforestation. The deforestation itself can also increase landslide risk by changing root strength, for example, or the way that triggering rainfall is intercepted. But we can also see processes that might actually decrease hazard, for example, afforestation, which can increase slope stability. I, in particular, am interested in how hazard might change with response to rainfall. And so there's an emerging number of case studies in the literature that have looked at quantitatively how slope stability is changing through urbanization with respect to rainfall. And so I'd like to share one example of that with you. This is in a study that was conducted by Eliza Bozelan, published in 2023 in Science of the Total Environment. And she used mechanistic modeling on the Caribbean island of St. Lucia to see how urbanization processes might change how hill slopes respond to different rainfall scenarios. So she takes slope units across the island, forces the model with a given rainfall scenario, and looks at the difference in response between forested areas, where we can see in the model, we have perhaps a more adjusted slope, it's forested, to urban areas where some of these processes like slope cutting to make room for building houses, create steep local slopes, loading the hill slopes with buildings, some other processes like runoff from impervious surfaces, and looks at how those two different categories respond. And what she finds is that in urban areas, the failure rates tend to be much higher than in forested areas. So this suggests one way that urbanization activities might actually increase hazard by changing these hill slope responses. This then leads to situations like this. This is an example of an urban landslide that occurred in Medellin, Colombia. And you can see some of these processes going on here. So this is a very steep slope that was likely steepened even further to build this road. We have loading through houses, maybe even some runoff from the roofs or other impervious surfaces that may have contributed to triggering this landslide. And then we have landslides in these very densely populated urban areas where the risk is highest. So engineering measures to stabilize slopes can work on a local scale, and we can even imagine scenarios in places with a lot of engineered slopes like Hong Kong, where urbanization activities may actually increase the stability of the slopes overall. But in other places where you can't necessarily stabilize slopes everywhere, one of the ways to reduce risk is through landslide early warning systems. And so in this talk, when I talk about landslide early warning systems, I'm referring to what people call geographical or territorial landslide early warning systems, which refer to trying to issue a warning over a broad region. So perhaps a city, perhaps a state, or even national scale. This is an example of a landslide warning dashboard from the small town of Sitka, Alaska in Southeast Alaska, which I had a chance to contribute to as part of my PhD project. You can see Patton et al. And Hess for the details of this. But it, like many landslide early warning systems, tries to estimate the current landslide hazard or probability based on a rainfall forecast. And unfortunately, unlike Sitka, very few metropolitan areas worldwide have currently operating dedicated landslide early warning systems. And so this is a figure from a review by Guzzetti et al. In 2020, where they looked at landslide early warning systems across the world. And this is a very dense figure, so I'd like to just focus on the map. You can see the publication for the further descriptions. And each of the points represents some sort of landslide early warning system. Red are regional systems, blue are national scale systems, and the pink global system refers to the NASA LASA model. And we can see that, so the green points represent reported fatal landslides from the Fruit and Petley inventory, and we can see that there are many areas with reported fatal landslides that don't have coverage by an operational early warning system. And to understand some of the barriers to that, let's dig into how these systems work. So most landslide early warning systems, in a very simplistic, this is a simplistic overview of how this works, will take a weather forecast. So we have forecasted rainfall across some region, and combine it with a rainfall threshold. And there's all sorts of different thresholds that have been explored. One of the most common is the rainfall intensity duration threshold. And with this type of threshold, we would take rainfall duration, so how long it's expected to be raining during a storm, look at the average intensity over the storm, and try and delineate an area where landslides are less likely and landslides are more likely. So given a weather forecast, we can say, okay, I think it's going to rain for 10 hours, and I think that the average duration or the average intensity will be 10 millimeters an hour. Okay, this might be an area when landslides are more likely. And these kinds of thresholds can then inform whether or not a warning would be issued. And so determining these thresholds has been a key line of research over decades. The first global threshold for shallow landslides and debris flows was proposed by Kane in 1980, so about 44 years ago now. And what Kane did, which is a little how-to guide on how to estimate rainfall ID thresholds, is first to collect landslide inventory data and precipitation measurements, and then to, using that inventory, determine the intensity and duration of the landslide triggering rain. So these then get plotted on this plot. We have duration on the x-axis, we have intensity on the y-axis. Each of these individual points is an observed landslide event. And then apply some method, and there's been many methods explored in the literature to delineate landslide triggering conditions. So in the most simplistic sense, we can draw a line beneath the previously reported landslide events and say, okay, we didn't see any events in this rainfall range. We have seen events in this rainfall range. This is a time when hazard might be highest. And I'll add the caveat that although ID thresholds have remained popular in the research, they're not always the best choice for operational warning. And you can see Bogart and Greco in NHES for details on that. But they are, I would argue, a valid way to characterize landslide triggering rain. So that's what we're going to work with in this talk. So one of the barriers for why few metropolitan areas worldwide might have these warning systems is that they lack sufficient landslide inventory data to determine these thresholds or to estimate these thresholds. But we know that there's a lot of cities out there that might be interested in having such a warning system. And so this raises the question of what such a city is to do. Do you take one of these global thresholds, but we had the background that the urban areas may be different than rural areas, so does this apply? Could we maybe borrow a threshold from a neighboring city or another region with a similar climate type? And these are some questions that we can discuss. So I'll start with the update of Kane. So there have been a number of other global thresholds, so maybe this would be an option. The most recent update of the global threshold was done by Guzzetti et al. In 2008. So we have Kane here on the left, we've got the Guzzetti update here on the right, and they took lots of reported landslides from different studies around the world and their intensities and durations as reported in those studies, and estimated a new threshold. So the Kane threshold, this first one, is up here in green. The updated threshold by Guzzetti is here in Blue and in between are some other proposed thresholds. So we can already see that compared to Kane, we've had a decrease in the threshold, which may reflect just a wider number of data points or that they include a number of mixed land use types, whereas the Kane study was mostly focused on a small sample of rural areas. Towards the question of could we maybe borrow a threshold from another region? Well, at least in the literature, thresholds have really been found to vary widely between regions. So these thresholds have been explored for many different regions at different scales, from Southern California to all of Italy, looking at Japan, or the city of Tegucigalpa in Honduras is this example. Got it all was for Seattle. And the common interpretation that people have taken away from comparing these studies is that regions with wetter climates tend to have higher thresholds. And this makes sense if we think that hill slopes are likely adjusted to local climate conditions. So if we frequently have rain of a given intensity, that's a normal storm. If a hill slope were going to fail during that storm, it probably would have already failed. So we would maybe expect that thresholds would be higher in places that are generally wetter. And the implication of this comparison is that very localized thresholds are needed. Now, when I started digging into this, I also noticed that previous studies have really used a wide variety of methods to identify thresholds, and also the landslide triggering rainfall, which I find really complicates the comparison. So something that would also be desirable is to have one common methodology that actually compares thresholds between cities. Then we can rule out that there's actually just differences in the methods. Okay, so against this background, what's a city with a landslide problem, but little or no landslide inventory data to do? Global threshold, we're not sure if it might apply in an urban situation or in their particular urban situation. We might want to try and borrow data from another city, but it's really unclear that this is valid. Thresholds have been found to vary a lot. Where does that leave us? And so that is what led me to the research questions that I wanted to look at in this study. So my first question was to ask, is a global rainfall threshold for urban areas different than previously proposed global thresholds from mixed land use types? And second, how variable are rainfall thresholds between cities worldwide? And can we get any handle on what might be driving that variation? So to go about this, I used a approach just like we talked about before, first collecting landslide inventory data and precipitation data, determining intensity and duration of triggering rainfall, and then using a method to determine the thresholds. And so I'll step you through how I approached each of those. First, I collected publicly available landslide inventories worldwide. So this is a plot of 12 different inventories from global scale, like the NASA Global Landslide Catalog, national scale, for example, the Geoscience Australia Landslide Search, or even regional or city scale, like the Kentucky Landslide Inventory or the City of Seattle's inventory. And then I subset these to landslides that had a documented precipitation trigger so that we can rule out that they were triggered by anything else, that occurred in an urban area as defined by the Global Human Settlement Layer Urban Center database. And so these are really densely populated areas. That database defines urban areas based on a population model and satellite imagery. So we're really looking at very urbanized areas here, and where we know the landslide location with a spatial uncertainty of less than 25 kilometers, so we can be pretty sure that it did occur in that area. And so the first result that I can share with you here is, where are these cities with reported landslides? So on the top map, we see, scaled by the number of reported landslides in this inventory that I compiled, cities with reported landslides in brown, and then all other cities where we don't have any reported landslides in gray points. We can see that Seattle and Medellin are the cities where we have most reported landslides, over 1,000, whereas with other cities, we may have fewer. And it's interesting to me to see what are the characteristics of cities with landslides. And we can do that by looking here at the bottom panel, the log odds ratio. And the way to read these plots is that they're a way to compare cities with landslides to all cities by their distributions. And so if the landslide cities were just randomly distributed among all cities, we would see just a flat black line here at 0. If in a given bin, cities with landslides are more frequent, we have a positive value, and if they're less frequent, we have a negative value. So for example, with mean annual precipitation, we see that in very dry cities, landslides seem to be less probable than all cities, but at some higher precipitation, mean annual precipitation, then we start seeing landslides. Similarly, landslide cities are more frequent in equatorial, temperate, or polar climate zones, and less frequent in arid or snow climate zones. Very low relief cities don't frequently have landslides, but you don't actually need that much relief to start getting landslides. If you have some relief, there may be some reported landslides. And we also see that in this compilation, landslides are less frequent in low income, lower middle income, and upper middle income countries, and more frequent in higher income countries. And this points to a potential source of bias in the data set that landslides seem to be more often reported in high income countries. It's likely that we're missing more landslides in lower income countries. And so that's definitely something that can be improved. So if we then take the reported landslides in urban areas, and I combined this with the global sub-daily rainfall data set, this is a hourly global station-based data set that was compiled by my collaborator, Liz Lewis. And this combination gives us 26 cities where we have at least 5 landslides with available rainfall data. So then for each landslide, I take the precipitation time series. So this is an example of a landslide that occurred in Seattle in 2010. We have precipitation over time. The red box indicates the day that the landslide occurred. And we find the peak intensity on the day of the landslide, and we start looking backwards until we find a 48-hour dry period. That's how we determine the length of the event. That's a modeling choice. Other people make other choices on how to determine what constitutes a rainfall event. And then the cumulative amount of precipitation over that time period, over the duration, gives us our average intensity. And so that's what we need to develop our thresholds. And so the method that I've used to develop these thresholds and to estimate these thresholds is called Bayesian multi-level quantile regression. And so I'm going to step you through that modeling approach and try to discuss some of the advantages that it has here. So first, starting with quantile regression. So in this schematic, we have, again, rainfall duration on the x-axis. We have rainfall intensity from gentle to heavy on the y-axis, and each of these points is a reported landslide, which has some duration and some intensity, like we just determined. Now, you might be familiar with linear regression. What linear regression tries to do is find the mean through a data set, and what quantile regression tries to do is similar, but it tries to find a quantile through the data set. So the median, which would be, instead of regressing through the mean, you regress through the median, would give you a 50th percentile quantile. So half of the landslides would have been triggered at intensities or durations above that, half below it. But we can also do other quantiles. So for example, a 10th percentile would be that 90% of the landslides were above, only 10% below. Or a 90th percentile would mean that 10% were above and 90% were below, so these would be the most extreme landslide triggering events. And like any line, this has a slope and an intercept. Those are the 2 parameters that we're going to estimate. So our slope, beta, and the intercept, alpha. And I work with standardized data, which means that instead of the intercept, instead of referring to where the line crosses The y-axis refers to the global average rainfall. Okay, multi-level models. So a multi-level model is what I like to think of as a Goldilocks model. So it's the just right option. So some different options that we could have would be, first, the pooled option. So this would mean that we would take all the data from all the cities and just fit one model and find a global threshold. This has some disadvantages because it gives a lot of weight to cities with a lot of reported landslides and maybe ignores cities that have fewer reported landslides. And it doesn't give us any information on the variation between cities. So that one was maybe like a little bit too cool. And then we have unpooled option, which would be that we just fit one model for each city individually. This, however, would not give us a sense of the global distribution of these thresholds. And then we have the just right option, the multi-level option, which is within one model, we are able to learn this set of parameters for each city, while we also learn the distribution across cities. Okay, what makes this Bayesian? Bayesian inference in a nutshell. So all Bayesian inference starts with Bayes' rule. Bayes' rule defines the posterior, which is a set of parameters here, capital theta. The probability of your parameters conditional on your landslide and rainfall data. So this means that we're going to get a distribution of thresholds, not one best threshold, but a whole probability distribution of thresholds weighted by their probability. This is a really nice way to represent threshold uncertainty. And this is a function of a likelihood function and a prior. And what the prior does is allow us to incorporate prior knowledge gained from previous research. And this whole thing is then averaged by the probability of data, which just essentially makes this a valid probability distribution. And so this is nice for our application because we get this intrinsic quantification of our parameter uncertainty, and we're also able to update the prior knowledge of ID thresholds, which was gained through previous research. So we actually include these prior thresholds in the model and don't need to just start anew. So getting then to the model structure, we have our quantile regression schematic, and for each city, we're going to learn a set of parameters, a slope and an intercept for each quantile modeled. And all of these parameters are modeled jointly. So we have here our parameters on the x-axis and on the y-axis, and each city will have a parameter estimated, and then we'll have also the mean of the entire distribution of cities, and that's what we then will consider our global thresholds. Okay, so Bayesian multi-level quantile regression, it's a nice way to estimate intensity duration thresholds. I would argue it allows us to incorporate prior knowledge from previous global studies and see how much we've learned. We can intrinsically quantify parameter uncertainty, which is a big advantage here. If you noticed before, very few thresholds report any kind of uncertainty. And we're able to model this variation between cities while also estimating a global threshold, which helps to answer the research question. Okay, so we do this modeling exercise, and what do we find? So first, I'd like to share with you the global rainfall thresholds for urban landslides. So this is our average across all cities. We estimated a 10th percentile, which indicates our least extreme landslide triggering rain. So 10% for each city, and estimated 10% would be below and 10% would be above, or sorry, 90% would be above. We have a median threshold, or 50th percentile, which would split the landslide observations in half. And we have a 90th percentile, which represents our most extreme landslide triggering rain. And so let's see how our estimated thresholds compare to our prior knowledge. So here in blue, we have the prior global threshold. That was the Guzzetti et al. Threshold, which combined data from a number of different land use types. And then for reference, we also have the pioneering global threshold by Kane, 1980, here in green. And what we can observe is that, in particular at shorter durations, our estimated urban threshold is lower than the prior threshold. So that indicates that less rain was needed to trigger those reported landslides than the prior threshold. We also see that the earliest, that the 90th percentile is lower even than Kane's first threshold. So most urban landslides are triggered at intensities that are lower than that Kane threshold. He may have only been capturing really the most extreme events. Okay, we don't only get the global thresholds, we also get different thresholds for each cities. And of course, you won't be able to see all of this now. You can eventually look in the supplementary of the paper, but we'll focus on a few. So one of the things that I wanted to be able to do was compare rainfall thresholds between cities. And the way we're going to do that in this talk is to focus on the median. So this is the middle of the road landslide triggering rain, about half for a given city, half landslides below, half landslides above. And the way that we're going to compare them is using a metric called credible distinguishable. So a posterior distribution is credibly distinguishable from another one if they don't overlap, and we do that at the 95th percentile. And so this is kind of a way of doing statistical significance, except for it's nice because you don't need a statistical significance test. And so, for example, here we have thresholds that were estimated for Seattle. The global threshold is in darker purple. Kuala Lumpur overlaps the global threshold, and Rio de Janeiro is above. And we can see that Seattle's threshold is credibly lower than the global mean, whereas Kuala Lumpur's threshold is indistinguishable from the global mean, and Rio de Janeiro's threshold is credibly higher than the global mean. When we look at this across all cities, we see that this median threshold is actually not credibly distinguishable from the global threshold in 77% of cities. So we have here in blue triangles, so pointing down, thresholds which were credibly lower than the global threshold. So that's in Seattle, Medellin, and Messina, Italy. We have the thresholds that are above the global threshold in Rio de Janeiro and in Mumbai, India. And then the rest of the cities that we estimated thresholds for, we actually can't tell that they're different from a global average. Okay, so for the next way to compare between cities, I'd like to be able to look at this hypothesis of, well, maybe thresholds should be higher in cities with higher mean annual precipitation. And for this next plot, I would like you to imagine slicing the posterior distributions along this dotted line. This is the average duration of landslide triggering rain globally, and we're going to look at the posteriors just through that line. This is one parameter to be able to compare them to each other. So, whoops. So here's the Rio de Janeiro slice. On the next plot, we have here the same Rio de Janeiro slice, but those slices then also for all of the other cities, and the global threshold is here in the purple range. And so on the x-axis, we have mean annual precipitation. We can look at if at that intensity, the thresholds in a given city would be higher or lower than any other city or the global threshold. And so we again see that most cities are indistinguishable. That's what we were looking at before, but we also don't see any kind of trend with mean annual precipitation. And in fact, cities with the highest mean annual precipitation, like Kuala Lumpur, are not credibly distinguishable from cities with the lowest mean annual precipitation, like this is San Diego. So that's really interesting, and suggests to me that perhaps urban hill slopes are not adjusted to local climate, that basically this building and this anthropogenic signal might be basically freshening hill slopes to fail, and have kind of thrown this out of this climate equilibrium. We also compared thresholds across climate classes, maximum topographic relief. So might you have thresholds that would be higher in steeper cities, or UN income class. And we similarly find that they are surprisingly similar. So we can't see any clear trend that cities in any given climate zone or with any given relief might be higher or lower systematically than other cities. And so this might suggest that urbanization is having a harmonizing effect on rainfall thresholds. So this might be overprinting any natural environmental differences and really giving us rather a consistent urban signal. So how would this potentially work? So if we look at these two failed slopes as examples, the left one occurred in Pittsburgh, the right one occurred in the city of Guwahati in India, and these are places with different UN income classes, which might indicate different availability of research or of resources for slope stabilization efforts, different climate zones, undoubtedly different geologies and different soil types. But what's similar between these failures is we can see that in both cases, you have a failed retaining wall. And in both cases, you probably have a modified slope here to create a parking lot, here to create this footpath. And so for me, this raises the question, are we seeing the real importance of modified slope geometry? And so I'd like to connect this back to another mechanistic modeling study. This was conducted by Holcomb et al. In 2006, and they really tried to model step by step the impacts of changing slope geometry. So with loading, with cutting, with deforestation from the original forest cover. And what they found is really the most important factor there is slope cutting. What are the slopes? And so it's possible that we might be seeing that modified slope geometry, potentially through cut slopes or fill slopes, is causing slopes to fail at similar intensities and durations, kind of regardless of these underlying natural factors. That's a hypothesis to be tested further. So returning to my research questions, first, I wanted to know, is a global rainfall threshold for urban areas different than previously proposed global thresholds for mixed land use types? We find that at short durations, global thresholds for urban landslides were lower than previously reported global thresholds across land use types. And second, I wanted to know how variable are rainfall thresholds between cities worldwide. And we found that thresholds for most cities were not distinguishable from the global threshold, and that these thresholds were really surprisingly similar across climate class, topography, and UN income class. Okay, since we still have a little bit of time, I'd like to throw in a bonus research question, which is that I was really curious, now that we had the thresholds, how extreme is landslide triggering rain in cities? So are these really like the most intense events, or is this happening in moderate rainfall? What are we looking at here? And so I compared our thresholds to the annual maxima for each city. So basically I took the entire gauge records available in a given city and looked for each year at every duration, what is the most intense period of rainfall on record. So for example, here in Durban at 10 to the 0, that's 1 hour duration. These were, for every year on record, the most intense storms. So anywhere between maybe 12 millimeters per hour up to 100 millimeters per hour. And we do this across durations. And this is actually also how meteorologists determine intensity, duration, frequency curves. This is the first step of it, but because these records are a bit heterogeneous, we didn't do that. But we can at least put then the landslide thresholds in context. And we see, let's focus on Medellin here as an example, that many of the urban landslides are actually triggered during fairly moderate rainfall conditions. So the 50th percentile threshold, for example, is at most durations still well below the annual maximum intensities. And so this was another quite interesting, surprising finding, that these really aren't just extreme events, that we also are seeing urban landslides during relatively moderate rainfall. Okay, I'd like to end with some implications of this study for landslide early warning. So first, previous global thresholds that covered multiple land use types might be too optimistic for urban areas, which would lead to missed alarms. So if you were to, for example, use the Guzzetti et al. 2008 threshold in some of the urban areas that I looked at, there would have been a number of landslides occurring below those thresholds. But we also saw that many of the urban landslides were triggered during very moderate rain events, which means that our global thresholds would likely see quite a number of false alarms. So this is actually one future research challenge, is to maybe move in cities beyond the intensity duration threshold and develop methods that are able to hone in on the landslide triggering rainfall, for example, through considering antecedent conditions, and try and get a better separation between triggering and non-triggering events. And we, based on the finding that many cities were not credibly distinguishable from each other, this actually suggests that thresholds might be able to be transferred from one city to another, and that for cities without landslide inventory data, thresholds from other cities can likely inform warning efforts. This is something that I didn't thoroughly validate in this particular paper because that wasn't the focus, but this would really be something that could be explored further. All right, I'm going to pause on the references slide for a moment so that in the recording, actually, if you want, you can take a screenshot. I'll give you another second. In the recording, you can look back at it. Here's the second. Okay, great. So thank you very much. Thank you for the invitation and for listening. If you have further questions after our question and answer session, you're welcome to reach out to me, my USGS email, and yeah, I'm happy to answer questions and looking forward to the discussion. Thanks.